Afternoon, everybody. Welcome to hopefully, and it should be, a fun-filled afternoon of organic chemistry, Chem 170, with your host, me, Dr. White. Hi, everybody. Let me have a few announcements first. First of all, let me remind you, Thursday, right after lab, remember I'm going to switch labs and from Wednesday to Thursday this week only. After lab, I will send out the password for test number 4, our last test of the semester. Boy, where did this summer go? But anyways, I'll be sending out test 4, which will cover polymers, lipids, otherwise known as fats and oils and steroids, mainly fats and oils, and carbohydrates. And that will be test number 4. I mentioned yesterday the point breakdown, and that will be on Thursday. Now, I got a special surprise for you on Wednesday. Make sure you come Wednesday, because the special surprise is I'm going to take you on a tour of an actual chemical plant, which most people never, ever, ever get to see the inside. And I'll explain why. I guess tomorrow I'll do it. What did I say, Thursday? Tomorrow. And you'll find it very exciting. At least I hope you do. And let's see, that's one thing. Another thing is, if you look at D2L and you're missing a score for one of the labs that have already been turned in, except the one for Monday, which I'll grade later today, I hope, make sure you send it to me via email. If you can't upload it to D2L, because of the lab amnesty program I have enacted. So get it in as soon as possible so you don't lose 11 points. Labs are easy 11 points. I'll be honest with you. I don't grade like, how can I take off points? It's right, I'll give you points. So anyways, make sure you get your labs in. And what else is there? I'll have to think if it comes up. But this week, today and tomorrow, because I rushed through the lipids and the carbohydrate chapter so you'd have time to do the problem set, I'm going to sit back, slow down, and go over that again. Because for some reason, I never know why, and I think I possibly could. Students figure I'm doing good, I don't have to study for the 4th test. People don't do good on test number 4, which also translates to people don't do good on the stuff in the final that's on test number 4. And that's what I'll be doing today and tomorrow. All right, let's move forward. What I'd like to do first is go through the lipids problem set. Or before I do that, anybody have any questions? And I know the other thing I forgot to say. By Friday at the latest, I will have the final exam information like I've done for tests 1, 2, and 3. And the final exam will be comprehensive. Relax, students do good on my final, because all next week I will be doing review of the whole semester, Monday, Tuesday, and Wednesday. So that's the future. What I have planned for you, let's get going. All right, thumbs up, people. Do you see lipids practice problem on your screen? Thank you. My morning class, I have the world's slowest thumb up people. They've got to like, should I do it or shouldn't I? And eventually they do, but you guys are super. Thank you. All right, Dr. White got lazy. What's a lipid? He knows that's not polite, but I'll tell you anyways. That's a compound that comes from plants or animals, something that was alive, that's not soluble in water, but soluble in polar solvents. Now, name one type of lipid. Well, fat is a lipid. oil is a lipid and a steroid is a lipid. Now, you should know what's the difference between a fat and an oil. A fat is a solid or semi-solid at room temperature. A oil is a liquid at room temperature. If you don't believe me, if you have any vegetable oil in your house, go look at it. It better be a liquid unless you put it in the refrigerator. By the way, if you put it in a refrigerator, it will become a solid or semi-solid with time. You put it in the freezer, it will definitely become a solid. Now, what is yellow grease? Pig's fat. What is white grease? Another form or different quality of pig's fat. What's tallow? Beef fat. You should know that. Now, I had some pseudo fats I made here, or oils. And what is a fat and oil? It's a triester. And give the organic product or products the following reaction. First, sodium hydroxide water with this compound, triester, ester, sodium hydroxide water. You get the alcohol plus the carboxylate anion. You would have used to make that. And notice I have 3 different R groups. Each one of these esters forms an alcohol, which together makes glycerin. And the first ester makes this carboxylate anion. Notice the double bond is not affected by this reagent under these conditions. So I have it. And the second ester gives me this carboxylate anion and the third one here. Next, I do the same molecule, but acid and water. And again, you have an ester, 3 of them. And here you have ester plus acid and water. You learn this for test number 3. You get back the alcohol and the carboxylic acid you would have used to make that ester. So ester 1, we get this alcohol plus this carboxylic acid. Under these conditions, the double bond will not react. Trust me, I've done it. And second ester, this alcohol plus this carboxylic acid, and the third ester, this alcohol and this carboxylic acid. Now, let's look at this. If I take and react this pseudo fat with hydrogen and catalyst, what happens? Will hydrogen and catalyst react with an ester? No. I'll say that again in slow motion. Will hydrogen and nickel or any catalyst react with an ester? No. But a double bond, it will. Double bond hydrogen catalyst, you break the pi bond and each carbon gets a hydrogen. And notice I was nice enough to point out where you should look. And if you change the catalyst, guess what? Same thing. Now, in E, I have an ester reacting with steam. What is steam? Hot water. Remember, in chemistry, there's 2 ways to make a reaction go faster. Why? Because time is money, and especially in a chemical plant. The ones I've worked at, depending when you, the accounting group, we call them the bean counters, when they figure out what's the direct cost or what's the cost of a chemical we're making in a company, one of the important things is how long you are in a reactor. And depending on the chemical company you're at, that number is anywhere from $300 to $600 an hour. That's an additional charge tacked on to the price of what it costs to make that. So you try and keep that short. And therefore, how can you speed up a reaction? One is a catalyst, like acid or base. Did you know all enzymes are catalysts? Well, they are. Most of them are acid catalysts. Now, the other way you can speed up a reaction most of the time, it's a rule of thumb, which means it's true most of the time, it's not a law, is by increasing the reaction temperature. The rule of thumb that I teach in general chemistry, which is pretty accurate, For every 10 degrees increase, you double the reaction rate, how fast it goes. So if I make the reaction temperature go up, it goes faster. And therefore, if we go back to E, steam is hot water. And you learned earlier up here, up somewhere, acid and water, you get back the alcohol and the carboxylic acid you would have used to make that ester. We use an acid catalyst. So another way of doing the same thing is steam, which is hot water. And what you do is you get back the alcohol and the carboxylic acid you would have used to make that first ester. You get this alcohol plus this carboxylic acid. Second ester, you get this alcohol and this carboxylic acid. And third ester, you get this alcohol and this carboxylic acid. And that's how we used to call splitting, steam splitting at the company I worked at, because we did this reaction with different fats and oils to the tune of about 2 to 3 million pounds a week. That's a lot of carboxylic acids or fatty acids we were making. Now, for F and G and H, the question is, if you react like an F, yellow grease with acid and water, what do you get? Well, how do you react to name? No, for this class, yellow grease, white grease, and tallow. Remember, yellow grease, big fat, white grease, big fat, tallow, big fat. You use this where R sub S means when you saponify this or hydrolyze it, you get stearic acid. This would give you oleic acid, R sub O, and this will give you stearic acid. So first ester, remember ester, acid, and water, get back the alcohol and the carboxylic acid you would have gotten to make that ester. This one will give me this alcohol plus stearic acid. Now, on a test, if I ask you to draw the structure of stearic acid, do not put R sub S carbonyl OH. I'll mark it wrong. Then I want to see all the carbons and hydrogens. But here you can use the abbreviation when I start out with abbreviation. Second ester, you get this alcohol. Notice R sub O, so you get oleic acid. That's what this is. And the third ester, you get this alcohol, so you get glycerin, and you get stearic acid again. Now the problem asks, give the product or products. You don't have to write this down twice. You don't have to put a 2 down there, because I'm not asking for you to balance the chemical equation. Now, tallow, since you use the same triglyceride representation, you'll get the same molecules. And same thing with white grease. Now, if we do yellow grease with steam, which is hot water, we'll get the alcohol and the carboxylic acid we would have used to make that ester, and you get the same products as you do for acid catalyzed acid catalyzed hydration of a fat or oil. And same thing if you use tallow. Now, for sodium hydroxide, the saponification of an ester, you get this. Here's our triglyceride. Remember, I used the RS, RO, RS, SOS, and base and water saponification, get back the alcohol plus the carboxylate anion of the carboxylic acid you would have used to make that ester. And the first one, you get glycerin plus sodium stearate. That's what this is. Second one, you get this alcohol plus sodium oleate. And the third one, you'd get this alcohol. So you get glycerin, and you would get, again, sodium stearate. If you wanted to put a 2 up there, you could. You do not have to. And finally, here would be give the starting materials for the following. And you could either write it or draw it. And what do you react with sodium hydroxide and water to get glycerin, sodium oleate, sodium stearate. It's right up here. You could be tallow, yellow grease, or white grease. And finally, what is a surfactant? I hid that right at the bottom. I just thought of it the last minute, and I put it right down there. And that's a chemical that interacts at the surfaces of different things. All right, any questions about that problem set? Got my speaker on? All right, what I'd like to do is go back and cover first. Let's go through a little slower because I sped through it. The Chapter 15, Lipids and Detergents. This will help you for test number 4. And remember, when we talk about lipids, that's something that's a chemical that comes from plants or animals, and it's insoluble in water, but soluble in organic solvents, nonpolar, ether, hexane, even gasoline. Don't try that at home, please. Excuse me. Now, there are 2 types of lipids, saponifiable lipids and non-saponifiable lipids. And a saponifiable lipid can be hydrolyzed under alkaline conditions, that means base, to give the salts of fatty acids, carboxylate anions. And we have a name for these. You should know they're fats and oil. And I've worked in that industry, and I'll tell you later today a nice little story. Now, non-saponifiable lipids don't react with base and water. And this we call steroids, also known as your hormones. Now, when we talk about fats and oils, which we call triglycerides, and I showed you the triester, they are, you should know a fat is a triglyceride that is a solid or semi-solid at room temperature, and oil is a triglyceride that is a liquid at room temperature. For those who are wondering, room temperature by definition is 25 degrees C. Now, I'm going to modify from what we did the first time I showed you this, and let's look at the following. We have acid hydrolysis of an ester. You get back the alcohol plus the carboxylic acid you would have used to make that ester. So if I were to take tallow, which is beef fat, and react it with acid and water, what 3 things do you get? And I'm going to help you out. Help me out first. And this is your time to have some fun. What would be the 3 products you get from that reaction? Your turn. And when you're done, give me a thumbs up. Well, 2 people are done. We'll wait for the others. And everybody's done, so I better get to work. Now, remember, always look for what's different. What's not carbon, what's not a hydrogen, what's not a carbon-carbon single bond. Oxygens all over the place here. And this is an ester, this is an ester, this is an ester. Let's call this 1, 2, 3. If I do ester 1, I'll get this alcohol from this general reaction plus this carboxylic acid. If I do this alcohol, this ester 2, I'll get this alcohol plus this carboxylic acid. And finally, if I do the last one, remember there's 4 bonds to carbon always, I'll get this alcohol, but this will give me stearic acid. And for those who must, you could put a 2 there, but you don't have to. And that's what you get. Glycerin, that's the common name for this alcohol. Let's see, what's the IUPAC? I've got to think about it. That would be propane, propanol, it would be 1, 2, 3, propantriol, 3 hydroxyl groups, but everybody calls it glycerin. I've never heard anybody say it by a UPAC name. All right, let's get back. Well, let's do one more. For test 3, you learned if you did saponification of an ester, NaOH and water, you have an alcohol plus the carboxylate anion, because the carboxylic acid in the presence of base forms the carboxylate anion, and you form these 2 chemicals, alcohol and the carboxylate anion, the carboxylic acid you would have used to make that. Now, I'm going to let you try this one. What would be the 3 products for this reaction? Your turn. By the way, hint, and you try it now. I see one person done, but we'll wait for everyone. And for those of you who are not here but watching the video, make sure you try this on your own too. I've always been threatening to say I'll bring game show music, like when they ask on a certain question, Jeopardy, and they play that awful music. All right, I think everybody's done. So how do we do this? Well, first of all, what is the structure for tallow? Well, for my class, the way I defined it is this triglyceride or triester. And now if I react this with sodium hydroxide and water, which is really what we're doing here, because this is really this. And now I have 1, 2, 3 esters. The first one will give me this alcohol. Remember, you don't break carbon-carbon single bonds. Plus, I'll get the carboxylate anion of the carboxylic acid I would have used to make that ester, sodium stearate. And then the second ester will give me this carboxylate anion of the carboxylic acid I would have used to make that, sodium oleate. And finally, the last one, this ester will give me this alcohol, but notice this is R sub S, which you'll get more of this. So if you want, you can put a 2 there. I won't. That's why I make it as tiny as possible, so you don't really need it. And these are your 3 products. Now, this is called saponification. And when I was rushing through, I didn't have time to tell you the story. I don't know how mankind found out about it, but for many eons, our ancestors would take animal fat in a big pot or whatever and boil it up with lye. Lye is sodium hydroxide. How many of you have ever heard of lye soap? And lye soap is sodium hydroxide and water reacting with animal fat to give you sodium stearate and sodium oleate. When you do it in there, you get 3 products. You'll get glycerin, and you'll also get what? The 2 carboxylate anions, which I taught you, long tail, polar head, that's soap. And there's been theories, I don't know how true it is. How did mankind first figure out, this is how you make soap? Well, you think about long ago, way back, when our ancestors, like beyond the cavemen, but not far beyond, they learned how to cook meat over fire. What did they use for fire? Wood that they burn. Now, when you burn wood, the ashes are high in what's called the chemical old name, potash, potassium hydroxide. There's going to be some water coming down in that, and that would react to make this white salt. And somebody found out, who would clean my hands? And they figured out how to make it themselves. And in the chemical industry that I worked in, one of the products we sold was a mixture of sodium and sodium oleate, sodium stearate, which we called sodium tallowate. And it would be these small little pieces that were almost like rods. And they had a funny name, and I don't know how it came about, but those are called in the industry. Are you ready for this? Soap noodles. Well, I wouldn't want to eat it, but they call them soap noodles. All right, let's do one more with this. You take a carboxylic ester and react it with steam, which is hot water. You'll get back the alcohol plus the carboxylic acid you would have used to make that ester. And therefore, it's apropos. Let's use white grease, which is not named after me. And what would be the three products you get when you react white grease with steam? Your turn. Let's see, one of you is done, but take your time. Do it right. All right, I think everybody's done. What's the designation or the structure used for white grease, which is pig's fat, yellow grease, pig's fat, tallow, beef fat, and that's this triglyceride, triester. And steam, remember, is hot water. You don't have to write this there, but I'm reminding you. And you get the alcohol and the carboxylic acid you would have used to make that ester. And there's 1, 2, 3 ester. Ester 1 will give me this alcohol plus this carboxylic acid, stearic acid. Ester 2 will give me this alcohol plus oleic acid. And ester 3 will give me this alcohol. So you make glycerin. And by the way, if you look at a lot of over-the-counter things, and even makeups and other things, cosmetics, you might see glycerin in there. And this one will give me stearic acid again. So you could put a 2 there, and that's what you make. Now, when I was going through this, because I wanted to get through to give you time to do the problem set, I didn't have time to talk about a story from Dr. White. Now, I worked for a company, was called Unichem Chemical. I think it's called Vantage Group now. They bought it from Unilever. But when I worked, it was called Unichem Chemicals. It was 47th and Racine, right by the old Chicago stockyards, because that's where they got their fat from. But anyways, at one point, and we would do this reaction to the tune of 2 to 3 million pounds a week, which meant we made millions of pounds per week of glycerin and stearic and oleic acid. The stearic and oleic acid we sold to chemical companies and other companies that used it, like Neutrogena, for their soaps. But One day, the President of the United States called me up, or actually he came to my office, I think, and he came over because we were all in the same location in the south side of Chicago there. And Unichem Chemicals was headquartered in the Netherlands, but in the United States, the guy who headed up the company in the United States was called the president of Unichem in the United States. And he came to my office and said, you know, we're making a lot of glycerin. We could make a lot more money if it was designated kosher glycerin. Now, I'm not sure if you know what kosher means. By the way, if you haven't figured it out, I'm Jewish. The gang gives it away, Yiddish. But anyways, that's the language spoken by Jewish people who came from Germany and Eastern Europe. It's a mixture of German and Hebrew. That's Yiddish. My grandparents all came from Russia, all four of them. And I was lucky enough to get to know them until they passed away when I was in high school, late high school, early college. But anyways, so he said, can you find out if what we can have, and he wasn't Jewish, sell kosher glycerin? What do we have to do? I said, I'll tell you what you have to do. You either have to stop buying yellow grease or white grease or build a new plant. He said, we're not going to do that. I said, well, I'll check anyways. Well, it turns out I know where to check. And there are certain organizations that authorize or give their symbol, certifies the word I was searching for, different things that are kosher. And there are certain kosher laws. And number one kosher law is never have anything that came from a pig. And that's just the kosher laws that came up. I can understand if you think about it, the Jewish people came from Israel, desert area, very hot. And what do we want back in the long time ago? What was one of the meats that went bad and you got sick from long ago? Pork. And I'm sure that's how it evolved, but that's my own personal opinion. Now, I called up, there's an organization called the Union of Orthodox Rabbis, and they certify certain things as kosher. And I called and talked to the person in charge of certification and said, I think I know the answer, but my president of my company wanted me to confirm it. And I told him what we did and what he wants done. He said, no, you're right. But what's kosher? How do you know if something's kosher? Now, for me personally, and a lot of people in our country, even though many are not Jewish, kosher products are made to a higher quality. And I personally believe that because the companies are inspected that are certified kosher. Now, how do you know if something's kosher? You look at the label. Everybody see on their screen right now a bunch of images from the internet? And over here, a big circle U. Those are the symbols you find on different items, like food items, that tell you it's kosher. Now, depending on where you are in the United States or where you are in the world, there are different organizations and different symbols. Mainly in the United States, it's either the circle U or the triangle K or just the K itself. Now, what does that K stand for? And over here, well, this is the word kosher. Right here, this first one, this Hebrew you read from left to right. And yes, I can read Hebrew. And underneath the lines are the vowels, and these are the consonants. And this is pronounced kosher. And by the way, this whole thing is kosher lepesach. And notice they have the English. Now, actually, it's kasher, but in the United States, that became changed to kosher. And in different things, you can find these symbols on things. Now, if you don't think I'm telling you the truth, where is it? Can everybody see above my finger? There's a circle U on my water bottle. That tells me what the water in here and the plastic made to make this bottle was certified kosher by the Union of Orthodox Rabbis. Now, I'm not Orthodox, but Orthodox only eat and use kosher things, but I still will look around. Now, funny story, I had a student who was Muslim who they have a similar type of dietary laws, not exactly the same, but similar. They came from the same reason. And that's called halal, and I always pronounce it somewhat wrong, but they look for things that are kosher because they're also the thing about the pig. And so I was telling the students about what I just told you, and this was face to face, and she came up to me and said, "Oh, I didn't know about that. All of them. I wonder if I can still keep on eating my Oreo cookies." If you go and get, next time you're in a supermarket, pick up a lot of the packages of cookies. In the lower right, you'll see either a K or a circle U. I forgot which one was on Oreo cookies, and they are kosher designated. Now, where you will never find a circle U or a K is on pork and beans. No way. Now, that reminds me of an interesting story about the same time. And actually, since the company I work for used both tallow from beef and yellow white grease from pork, both fats together. And if we could get pork, yellow grease, white grease was always cheaper than tallow, we would. I told the president, you got one of two things. You clean out all your equipment real good. We only use tallow, which would make our expenses higher somewhat, you know, or you build another plant exclusively using tallow. And so we can't do that. And we didn't sell glycerin. By the way, chemicals and spices and other things that are kosher, designated kosher, certified kosher, command a higher price than those that are not, which you can make more money. Now, funny story that was in the Wall Street Journal years ago, about the same time I was doing this, right after, there was a Chinese company that was making spices for sold throughout the world. Excuse me. And they wanted a kosher designation. So they paid for one of the inspectors from, I don't know if it was Orthodox Union of Orthodox Rabbis, to come to China and inspect their plant. And as the article in the Wall Street Journal, the first time, and it was a rabbi who came out, a lot of the inspectors are rabbis, came out and inspected the plant, went to the owners and said, "I can't certify you kosher." And the plant owner said, "Why?" So, "Well, I went in your lunchroom and all your workers are eating pork and you've got pork on your site. I can't do that." And the owner said, "Well, come back in a couple months," and was able to train his workers or pay them or whatever, I forgot which, to stop bringing anything pork to his plant. He may have paid him more, who knows, I don't remember the exact. And the rabbi came out again, and also those people do surprise inspections once they do authorize it to make sure you are keeping kosher. And he did his inspection and found nobody was eating pork, and the plant was certified kosher, and they could raise their prices of their spices and make more money. And I thought you'd enjoy that story. And when I was rushing, I didn't have time, feel I had time to do that. Now, we talked about fatty acids. And let me get back to my slides. And fatty acids, so I'll never ask on tests, but I use the term that's shorthand for fatty carboxylic acids, or flows from fats and oils. They're always even numbered, never branched. And you should know the one, FA stands for fatty acids. Saturated fatty acid has all carbon-carbon single bonds. You should know this. And the one you should know is stearic acid. The structure of stearic acid 18 carbons, and instead of drawing out 16 CH2, I'll do it shorthand. And on a test, if I ask you to draw the structure of stearic acid, don't use the abbreviation R sub S, use this, and that's stearic acid. And say saturated fatty acid. Remember long ago, saturated hydrocarbons with only carbon-carbon single bonds, also carbon-hydrogen atoms, but the important thing was only carbon-carbon single bonds. Now, listen carefully. If I asked you what is a saturated fatty acid, and you put down a molecule with only single bonds, I'll mark it wrong. As you notice in stearic acid, you have a carbon-oxygen double bond. Saturated fatty acids have only carbon-carbon single bonds. Now, next, let's talk about monounsaturated fatty acids. And mono means one, unsaturated means it has a carbon-carbon double bond. Mother Nature never did it and never has done triple bonds. That's something organic chemists, synthetic organic chemists came up with. And one example you should know for a monounsaturated fatty acid is oleic acid. And on a test, if I asked you to draw the structure of oleic acid, it's 18 carbons, has one double bond. It can be sister trans, and for this class, you don't have to put sister trans. And remember, the double bond starts at C9. Remember, this is one, and then 7 more makes this one carbon number 9. That's why I mean by C9, and then the rest of it. And this is oleic acid. And when I worked at Unichem Chemical, I looked up earlier, they're still selling it under the name Vantage. I developed 2 new grades of high purity oleic acid, Priolane 6906 and 6907. I think it's been years since I thought of that name. But on a test, you should know the structure of oleic acid. Don't put R sub O, carbonyl OH group. You have to draw out all the carbons like I have here. And this is oleic acid. Now, I won't ask you what a polyunsaturated fatty acid is, but you have 2 or more double bonds like linoleic, linolenic. Oh no, guess what time it is? It's time to take a 5-minute break, and I'll see you at 1:50. So I'm gonna get up and stretch. Be right back in 5 minutes. time to get started again. Now, in a double bond, in a fatty acids like oleic, you have a double bond. And that double bond can be cis or trans. And where does that fatty acid come from? From a triglyceride, where the R groups like R sub O, R sub S. So that makes the fats cis or trans. And I think you've heard about in our, I don't know if you heard, medical science has told us that trans fats are bad for us. And a couple of years ago, a number of the food companies, and including McDonald's and other companies that sell prepared foods, switched to all cis fats. Now, as I've mentioned, beef fat, you should know, is tallow. And you don't have to know, but BFT stands for bleachable fancy tallow, which is the highest grade purity of tallow you can buy. And you should know pig's fat, there are two types, yellow and white grease. And you should know that. People who don't know the chemical industry, like whoever, I actually know who wrote the book, we were using that book, call it lard. No, it's white grease or yellow grease. And I showed you where these are in the breakdown in different things, in vegetable oils and butter and beef fat and stuff like that, the different fatty acids you get from acid hydrolysis of those fats and oils. We did hydrolysis with steam. We did saponification with steam. But let's look at hydrogenation of a fat and oil. Not me, wrong place. Let's get to the right screen. Long time ago, you learned double bond in a catalyst. Catalyst can be nickel, platinum, or palladium. And what happens is you break the pi bond, and each carbon of the double bond gets a hydrogen. And let me tell you, hydrogen in a catalyst will not react with a carboxylic acid. Again, hydrogen in a catalyst will not react with a carboxylic acid. And the question is, what's the product or products of that reaction? Your turn. And the thumbs are coming up. And if you haven't finished, I will wait. All right. What's different? Look at a molecule. What's different? Well, you got oxygen here, but that's a carboxylic acid. That won't react with hydrogen and catalyst. Oh, look, we've got a double bond, and that will do that. Do you break carbon-carbon single bonds? No. The only change will be with these two carbons. And what happens is I'll break the pi bond. And each carbon gets a hydrogen, and I'll write the rest of this. And I could remember this is now CH2. This is now CH2. So I've got 7 here, 14 plus 2 here at 16. I could rewrite this like this. And you can convert oleic acid into stearic acid by hydrogenation. And I did, or a company I worked for did. Actually, I helped improve the process of this reaction greatly and get a higher purity too of stearic acid. Now, with that in mind, what would be the product or product of that reaction? Dr. White's getting sneaky. Well, I see some people are finished. If you're finished, or if you want me to go ahead and do it, you can also do a thumbs up. All right, what's our Sabo? This right here. And what does it become? This molecule. And what's this? R sub S. So the answer here is this. And once again, this is oleic acid. And it becomes stearic acid when you hydrogenate it. And now for the grand finale. Ta-da! It's Awful Humor Tuesday. And here's the final one. What product or products would you get with that reaction? And almost everybody's done, but I will wait. Everybody's done. Now, hydrogen and a catalyst will not affect esters. It won't. Whoop, let's get it right. And I have my 3 esters. Now let's look at R sub O. What is that? That's this, and that double bond becomes that, which is R sub S. So immediately, this R sub O and this one become R sub S. Now this R sub S is this right here, which is this right here. It's got nothing that can react with hydrogen and catalyst. So guess what? I get back R sub S, and this is what we call a hydrogenated fat or oil, which medical science has said is bad for your heart. Now, why did they do that? Well, they've changed it slightly, but for many years, if you take, and a lot of times, this is really R sub O also, you take vegetable oil, which is highly unsaturated, a lot of oleic acid groups in, or allelyl chains in here, R sub O, and you hydrogenate it, you get a hydrogenated fat and oil. Now, when you change that R group from a double with a double bond to no double bond, you get something that's a liquid at room temperature to something that's a solid or semi-solid at room temperature. Why would you do that? Well, if you mix it with a little yellow pigment, some water, and some flavoring, we call that margarine. And you can charge a lot more per pound for margarine than you get for vegetable oil, and you make a lot of money. Now, time for a special Dr. White story again. Now that I have time to do it slowly, I had to skip these stories before. When I was at Unichem Chemical, I was the senior manager. I was laboratory manager for all of North America. And because of that, Unichem was part of a larger international company called Unilever. And once a year, they got all the senior managers, technical sales, and everybody together for a get together. They had different presentations, but more of it was to get to meet other people in this multinational company. So if you had a problem, you could go to another division of a company because you knew that person. You met him at this getaway or conclave, and you could ask for help. And you also built good relationships. Well, the one we had was up in I think it was the Catskills, upper New York State. It was a beautiful resort. I mean, it was beautiful. We had these sort of like cabin suites. Each cabin had 4 bedrooms, each the size of a huge suite. I mean, it was huge. You had your own bathroom and everything. And then they had a place where we all ate dinner and lunch and breakfast. And it was like being on a cruise ship. I actually gained weight, and I wasn't the only one. Plus, was all the alcohol you could drink, and it was free. The company paid for it. Well, I still remember the first day, we're all together, about 120 of us or so, in this big room, conference. It wasn't really a conference room, it was auditorium or room. And every once in a while, the owner would come in and say, I got an urgent call for so-and-so. This was before cell phones. And yes, there was a time before cell phones in our life. And it was after the color TV was invented. But anyways, and this one manager would run out and get the phone. and come back. And 10 minutes later, the owner would come back and, where's so-and-so? I got an urgent call for you. And he'd let. 15 minutes later, same thing happened. After about 5 or 6 times, uh, the person who was in charge of it, a senior vice president for Unilever, said, stop, and said to the guy, go back to your office, whatever it is you're needed there. It's more important than you being here. And so take a flight out and leave. You're needed. And he did. And it took me a couple weeks, and I finally found out what was the emergency this manager had to deal with. Well, he was the marketing manager for a new product Unilever was going to sell to the United, bring out, roll out, as they call it, to the whole United States. And that product was, I can't believe it's butter. And they had something like 300,000 cases and 24 in a case, a lot of product. And somebody, after they'd made it and they're about to ship it, decided, let's open a case and look at some of the products. And they found out when they took the lid off, the foil on top of the container was bulging. It was like inflated, like a balloon, a little balloon. Something wrong. And that was the problem. And turned out it was nothing hazardous or anything. I don't remember what was causing it. And the solution was they hired a bunch of high school kids, gave them syringe needles, poke a hole in there, put the gas out and cover it and ship it. And they shipped it. Nobody got sick. And it was a funny story. By the way, if you don't know by now, chemists know how to party hard, especially when it's on company money. Did it at Unichem, did it at Unilever, or at Axo, and Borden Chemical, we did it too. Ooh, we don't ask me about that one time in Louisville. All right, that's hydrogenation. Now, how does soap work? There are 4 things I expect you to know leaving my class. And one of them is, how does soap work? And you should know soap has a hydrocarbon tail or nonpolar tail, polar head. And remember, like dissolves like. And the following you should know. Know this. You'll be happy that you did learn this. And when you wash your hands, things you should know. You should know the structure of soap. I haven't asked, but thumbs up, people. Do you see how does soap work on your screen? I'm writing it. Thank you. All right. Soap, you should be able to draw. It has a nonpolar tail. That's what this means. Lots of carbons, CH2, CH3 at the end, and a polar head. Now, they're different polar heads. And the one I've talked about already is R sub T, like this. And what's R sub T? It's a mixture of R sub O, oleic acid. Actually, I take this back. It's actually a carboxylate anion, sodium oleate, which is a mixture of sodium or sodium taloate, which is a mixture of sodium stearate, oleate, and sodium stearate. And you know these R groups are long. This one has the double bond, this one doesn't, but they both mix together, make R sub T. And now, the important thing you should know so important. I'll draw it in large font, like dissolves like. And that means polar things are soluble in polar things, non-polar things are soluble in non-polar things. What's the most polar substance in all of our world and chemistry? Water. It's polar. When you're trying to clean things, what are the two main things? Dirt and grease, which are non-polar. And if I have a magnified piece of dirt, like the one that was on my hand this morning, not really, but pretend, it's non-polar. And if I have water, it will look at that and say, oh, you're non-polar, I'm polar, like dissolves like, I want no part of you. And it won't clean it off your hand. Now, how do you get it off? You use soap. And now with the soap and water, and when you rub your hands or like you should to get them nice and clean, what happens is the non-polar tail looks at dirt, and the non-polar tail of soap says, oh, I'm non-polar, you're non-polar, I'd like to be close to you. But the polar head says, oh, like dissolves like, I want to be as far away from you as possible. And a lot of these do this. Lots of them, so it totally surrounds the dirt particle, and we call this now a micelle. And you should know what a micelle is. It's a dirt particle surrounded like that by soap. And now water looks at the micelle and says, only sees the polar heads here. And says, oh, I'm polar, you're polar, let's go down the drain together. And lo and behold, your hands are clean. And let me just show you what a micelle looks like with a slight cutout. And this is a micelle. The blue part are the polar heads. The plus charge are the sodium cations floating around. This is water, the squiggly lines. If you take a cross section out, you can see right in the middle here, the dirt particle. Well, that's where the tails all come together. And these long non-polar tails want to be near that, but the polar heads want to be far away. And that's a micelle. And that's how soap and water works. Now, I won't ask on a test, but we'll go through it on Thursday. When you have a detergent for your clothes, that's linear alkyl benzene sulfonates. This will never be on a test. And that's an awful looking benzene ring. And here we have our polar head. And here we have, this is R with 9 to 12 carbons plus a benzene ring, our non-polar tail. And laundry detergent works just like soap used for your hands. The dirt and whatever grease on your clothes, you form micelles, and that's how it gets off your clothes into the water and down the sink from your, not sink, all your drain, from your washing machine. Again, same thing happens. Now, I briefly ran through There won't be anything on the test on phosphoglycerides, which are really triesters of uh, glycerin, and they're called phospholipids. And the most important one is lecithin. And here's the structure. You have oleal group and a sterile group, ester, and then you have this group. And this is your polar head, and these two would be your long non-polar tail. They show it bent on each other, but think of it more straight. And this is polar, this is non-polar. And where do you find lecithins? In soybeans and eggs. Now, personal thing, I think I mentioned it, but I'll mention it again because I've gotten back to it big time and it's making a big difference again. I get away from it every once in a while. I have to remind myself, Dr. White, it's time to get back to eating more soybeans. Now, tofu, I can take or leave it, but what I really like is the shell edamame, which is the soybeans, the green ones. And you take those, you buy them frozen, everywhere sells them now. And I boil them up for about 5 minutes once you let them thaw out. And then you can take them and freeze them again because now they're cooked. Grab a handful, put it in soup or whatever. I also make a soybean spread that's dangerous on crackers and other things. And because of the lecithins, it affects my brain and my body. I sleep better. I'm more mentally active or sharp, and it makes a big difference. Now, when we talk about surfactants, there are different types of micelles, but that's one of the things I mentioned. And vegetable oil is non-polar, water is polar. Just look at oil, vinaigrette dressing. Vinegar is mainly water plus, acetic acid. After you shake it up, put it on your salad, put the bottle down, it separates. Well, mayonnaise is vegetable oil, water, an egg, and usually an egg yolk, and seasoning, salt, pepper, whatever. But anyway, seasoning. Well, how does the egg yolk help bring the oil and water together to make mayonnaise? And hopefully you've seen mayonnaise. It's a semi-solid that's homogeneous, the same throughout. Well, the egg yolk contains lecithin. And if you ever look at lecithin, and I worked with it once, it's a yellow solid. And why do you think egg yolks are yellow? Because of that. And that helps the polar end get some water, the non-polar end gets some oil, and it helps make what's called an emulsion. And surfactants are great, what we call emulsifiers. And like I say, here used to make mayonnaise, you can actually buy it for food grade, or you can get chemical grade for reactions in a chemical plant. Now, I talked about the steroids, and the steroids are lipids that can't be saponified. And there are hormones. You should know how to draw this ring system of a steroid. And how do you draw it? Draw a six-membered ring. Think about it. 8 months ago, would you even know what I'm talking about? Six-membered ring? Now you do. Isn't it amazing how much we've learned? You've learned this summer? You should be proud of yourself. I am. All right, next, right next door, there's a fused, meaning they share the same carbon, six-membered ring. Then at 12 o'clock, this carbon here, you have another six-membered ring. And finally, right next door here, you have a shared, oh, my rings are bad. Let me do it. And you got 1, 2, 3, 4 rings. 3 of them are six-membered rings, and 1 is a 5. And you should know how to draw the steroid skeleton, which is that. And if you remember, I showed you some, which you don't have to know for the test. Testosterone, the male hormone, has that ring system. Progesterone, a female hormone, has that. And then estradiol, which is the female hormone that controls a woman's menstrual cycle. And then the modification that organic chemists made to inexpensive molecule hormone or steroid to make estradiol, which is your body, a woman's body can't tell the difference that and regular estradiol, and that's the active ingredient in birth control pills. All right. Everybody sees synthetic polymers on the screen? Thank you. All right. This I also somewhat raised true. If you notice, I didn't have any problems or problem set for this because there's not much I can ask in different questions, but I like to go through this so it will help you on Thursday. Now, first thing is, what's a polymer? And you should know a polymer is a macromolecule built by repetitive linking of smaller units called monomers. Think of it as a long freight train with boxcars as your monomers. You're linking together, and we call that a polymer. And macromolecule means really big, and I mean really big molecules. And poly means many, mono means one. I will never ask that on a test, but it's good to know. And mer means units, so polymers, many units linked together to form a macro or monster big molecule. Now, there are 2 types of polymers, or actually, I should back up here. I should put another slide in. There are 2 ways of classifying polymers. One is based on chemistry. When you do chemistry, there are 2 types of polymers: addition polymers and condensation polymers. I keep on hitting the wrong screen. It's Click on the wrong screen, Dave. All right, let's look at there are two types of polymers. The first one is an addition polymer. And this has, you know what I just realized I haven't done today? Boy, is my head screwed on backwards. I haven't done the full review. I sort of have, but let's finish this slide. And after the break, I'll do the full review for test number 4, but essentially I've been doing that. An addition polymer has one type of monomer. And examples of this rubber tire, and also saran wrap or plastic wrap in a kitchen. Those are addition polymers. Now, the other type is condensation polymers. And examples would be plastic bottles, like water bottles, pop bottles. Remember, Dr. White's from the Chicagoland area, and pop is that carbonated liquid that's non-alcoholic that you can get in bottles or cans. And another thing is anything nylon, like nylon jacket would be an example of a condensation polymer. And now I can go back and do what I should have done to begin with earlier today. We got plenty of time. I'll get you out before midnight. But first, oh, I'm so embarrassed. I was so gung-ho on we should go back and do some stuff. I forgot to do the review. So I'm going to start it now. We'll still take our break in a couple minutes, and I'll finish the review. And I'll go back to polymers. All right, thumbs up, people. Do you see test 4 review on your screen? Oh, I think it's time for me to take a summer break. Not really. All right, let's go through it. This is in the lecture file of D2L, secretly named test number 4 review. All right, you should know what a polymer is. As I just mentioned, deja vu all over again. It's a macromolecule made up of repeating units called monomers. When we talk about chemical properties of polymers, there's two types. Addition. Oh, I got it right. Only one type of monomer used: tires, rubber tires, and saran wrap. When it comes to condensation polymer, you have two or more different types of monomers used. Example, plastic water bottle. I didn't put down here nylon, whatever, jacket, or other things that are nylons. By the way, nylons were made originally when the inventor, they had made nylon for parachutes for World War II. And one of the chemists who helped develop that, because in World War II, they used all silk for parachutes, women couldn't get silk stockings anymore. And he made his wife some stockings instead of silk out of nylon. And that's how nylons evolved and eventually into pantyhose, which are nylons or nylon material. Now, the other way of categorizing a polymer is by physical type, a physical property. And there are two types. Thermoplastic, you should know, is a polymer. Once it's formed, like into a bottle or something like that, it can be reheated and reshaped to form a new polymer. And a plastic water bottle is an example. It can be recycled. Now, the other type is thermoset. Once formed, it cannot be reheated or reshaped. Example, this would be car tires or the foam in your car seats or insulation. I'll talk more about in tomorrow's lab, called the urethane foam. Those can't be reshaped or reheated. Now, when we go on to fats and oils, a lipid is a molecule from a plant oil, not soluble in water, soluble in nonpolar solvents. And we talked about saponifiable lipids, which are fats and oils, and they yield carboxylate anions of fatty acids when react with base and water. The non-saponifiable lipids do not react with base and water, and we call those the steroids. And some of this is going over again, but repetition is good for your grade. If you haven't figured that out all semester, I do that on purpose. If you have a fat or a fat, you should know that's a solid or semi-solid triglyceride at room temperature. And oil is a liquid triglyceride at room temperature. And here's one way of drawing fats. And I went through acid hydrolysis of an ester. And if you have a fat, you have this. And we did with R sub S and R sub O. Base hydrolysis or saponification of an ester. Here's the general reaction. And here's what you get when you do it with base. And you should know the structure of stearic acid and the structure of oleic acid. Also, you should know what is a saturated, what's a saturated fat and what's a unsaturated fat. A saturated fat has only, and it's important to say, carbon-carbon single bonds, because it has a carbonyl group in it. If you just put down single bonds, I will mark that wrong. And an unsaturated fat has at least one carbon-carbon double bond. Do not put down triple bond, because Mother Nature never made triple bonds. Now, I have a quick question I've always been wanting to ask, and I always forget, but I'll ask you because you guys are quick thumbs up people. Can you see the bar at the bottom of my screen that I see for Zoom with things like participants security? If you can see it, better yet, if you can't see it, give me a thumbs up. If you can see it, okay, you can't see it. I have to move it like on top or bottom when it gets in the way for me. And I always wondered if you can see it. So I guess the thing is you can't see it. All right, remember saturated fat, only carbon-carbon single bonds in the molecule. Unsaturated, only carbon has at least one carbon-carbon double bond. Now, remember white grease, tallow is beef fat, and white grease and yellow grease are pig's fat. And as I did this semester, I came up with the concept, let's use this right here, triglyceride, R sub S, R sub O, R sub S, SOS, save our ship. That's my inside joke, as a representation for tallow, white grease, and yellow grease. And therefore, if we were to take, like we did earlier, tallow, react with sodium hydroxide and water, you get three products. Remember, saponification of an ester. And if we look here, we have our three esters. They give us glycerin, plus this one gives sodium stearate. This one gives sodium oleate, this carboxylate, and this one would give sodium stearate again, which I have the two there. You don't need it. And that's that. And you should know the reaction of that with acid and water or with steam. Ooh, deja vu all over again. And that is, how does soap work? And you should know that soap has a nonpolar tail, polar head. Like dissolves like is the important part of this puzzle. What does that mean? Water is polar, dirt and grease are nonpolar. When you have dirt that's nonpolar, water won't look at it because it says, oh, I'm polar, you're nonpolar, stay away from me. I'm going to stay away from you. But when you use soap, you form a micelle because the dirt, which is nonpolar, attracts the nonpolar part of soap. The polar head stays away from it. And now water looks to micelle and it looks polar and says, hey, micelle, I'm polar, you're polar. Let's go down the drain together. And as I mentioned, I did a better job drawing this ring in this one. You should know steroids are this ring skeleton 6, 6, 6, and 5. Next, I talked about carbohydrates, and we're going to go through the problem set tomorrow. And I've got time to go through key things I rush through tomorrow, so you can do well on Thursday's test. You should know, what is a carbohydrate? A carbohydrate is a polyhydroxyaldehyde or a polyhydroxyl ketone or molecule upon hydrolysis, water becomes a polyhydroxyaldehyde or ketone. And if I look at the clock, it's time to take a 5-minute break. And I'll see you back at 2:50. Let's take a break. I'm going to replace the batteries in my brain. I'm back. Let's get going. All right. I put a new battery in, so hopefully my brain will be working now. All right. Let me remind you, tomorrow, instead of having a short lecture in a lab, I'm going to switch it. We'll do the lab on Thursday. Tomorrow I'll have more time. I'll go over carbohydrates and death. We'll also have a special surprise for you. I'll be going to a chemical plant and seeing the inside of one. It's an exciting place to go to. I know I worked in them enough. And that should take, and also I'll start some new stuff. So that's tomorrow. And I'll put out later today a email with an update to remind everybody about that. All right, everybody see the carbohydrates on your screen? Thank you. All right, now talked about chirality. You should know that chirality or chiral means handedness. Aren't you glad they didn't pick the Greek word for footedness? But anyways, and we talked about a chiral object is an object with a non-superimposable mirror image. I'll never ask you the definition, but I'll ask you to know how to do, is this a chiral compound or not, or object first. And we'll go through this tomorrow in the carbohydrate problem set. Next, achiral, the prefix A means without, and we'll talk about achiral objects. And achiral is an object with a superimposable mirror image. And tomorrow you get to see some more of my artwork. Oh no. But anyways, chiral object with a non-superimposable mirror image. Your hands are chiral, mirror images, non-superimposable. Achiral object with a superimposable mirror image. And if you had, well, we're not going to have one, but what if you had a perfectly round snowball? It would have a mirror image that would be superimposable. So perfectly round snowball would be a chiral object. Next, I talked about chiral carbons, and a chiral carbon is a carbon that has 4 different groups or 4 different atoms or a combination of 4 different groups or atoms. I'll never ask you what a chiral carbon is, but tomorrow in the problem set, and I'll go through, we'll have circle the chiral carbons. And I'll remind you again that, first of all, time out from some water, that if a carbon is in a double bond or a triple bond or has 2 or more of the same group, like hydrogens, it cannot be a chiral carbon. Next, I taught you about enantiomers, and that's a molecule with a non-superimposable mirror image. And I'll never ask you on a test what's an enantiomer, but as you'll see tomorrow, the problem set I can't ask you, draw the enantiomer of this molecule, and that molecule being the mirror image of that molecule would be the enantiomer. Now, you should know that this reaction from test 2, take an aldehyde or ketone, alcohol plus acid catalyst, you form a hemiacetal or hemiketal. Now in glucose, since you have the alcohol here at C5, and the same molecule with the aldehyde up here, you don't need a catalyst, and it's in equilibrium, and this attacks that and forms a bond to that carbon. Everything else stays the same. This opens up, like this carbon here, the hydrogen hydroxyl group. Now, that's for glucose. And on a test, you should know if I give you this and the double-headed arrows, you should know how to draw this product. If I give you this product in double arrows, you should know, is this a compound? Or you could put down glucose. And this similar thing happens with fructose. And fructose, you have this hydroxyl group again in C5, 1, 2, 3, 4, 5, which is the alcohol up here, attacks the carbonyl and forms this hemiacetal, or in this case, hemiketal, and everything else stays the same. Now, once you form this glucoside, or yes, glucoside is the glycoside of glucose, the cyclic form, which is really this hemiacetal or hemiketal, with another alcohol and acid catalyst, you form an unsymmetrical acetal or ketal. And in the case of this cyclic form of glucose, you would take any alcohol and acid, you replace the OH on the carbon up here with OR here. And as I showed you yesterday, this is how Mother Nature takes these cyclic form of glucose and bonds them together to make starch. And the next slide, I show that. First of all, you should know table sugar is sucrose, table sugar being the white stuff, at least I put in my tea. I don't know where you put it on, maybe on your cereal or whatever when you cook. And that's made up of fructose in a cyclic form bonded to glucose. And starch is a polyglucose molecule. But you never thought of starch as being a polymer. Now here we have glucose reacting, a lot of them together with acid catalyst, we call an enzyme, to make starch. And note the linkage is an acetal or ketal bond. And remember, sucrose is fructose and glucose held together in an acetal bond. Acid and water, which comes from your stomach, breaks it back down to glucose and fructose. So again, sucrose, acid, and water become fructose and glucose. Now starch, like if you had French fries, potato chips, or pizza, all the things I don't need, when you chew it and swallow it, it becomes glucose. Now, leaving this class, there's a couple things you should know. How do you describe with words and a general reaction what happens when you, and you do this for test number 4, you should know when you eat something that has a fat or oil in it. What's the functional group in a fat or oil? Ester. Therefore, when you chew it, I don't know, did I ever tell you the story? I don't think I told you a story. When I was real little, like real little, my mother used to say, chew your food before you swallow it or you'll choke. Guess what? She wasn't lying to me. I did choke one time. In case you're wondering, I survived. But when you chew your food and swallow it, it goes down into your stomach. And what's in your stomach? Water. And one of the miracles for me personally of life is I have, and you have, cells in your stomach that make, fancy word is synthesize, hydrochloric acid, H+. And that water and acid helps break down the food you eat, which I always find astounding. I have that in my body that makes that. And when you eat a fat or oil, it's acid hydrolysis and the functional group of an ester. And you should also know how to write the general reaction. Ester, acid, water, you get back the carboxylic acid plus the alcohol you would have used to make that ester. And then you should know, if you eat a carbohydrate, what happens? How do you describe that with words, general terms, and a general reaction? And what's the functional group that holds glucose together in starches, which are carbohydrates you would think of? And that is an acetal. And as you, hopefully you chew your food before you swallow, like my mother taught me, and it goes down into your stomach where there's acid and water, acid hydrolysis of an acetal. And this is a general reaction, acetal or ketal, acid and water, you get back the aldehyde or ketone plus the alcohol you would have used to make that acetal. Now that that bar is gone, I wish I could shut that off. But anyways, if you have an at the very bottom, acetal or ketal, acid and water, H plus is acid, you get your acetal or your ketone you would have used to make that acetal, ketal, plus the alcohol. You don't have to put the number 2 there, because chemists don't bother balancing equations when we don't have to. All right, that's the review. First of all, let me ask, any questions so far? And by the way, I have done the same thing I did today in a face-to-face class where I forget to do the review. I just want to go back and do some stuff that I rushed through, and that's happened before. All right, let's go back to polymers and finish that up. And there are 2 types of polymers. I talked about addition and condensation. Let me see if, let me do this. We're talking about the different types of polymers. Instant replay. When you talk about chemistry, there's an addition polymer. Everybody see that on their screen now? Just checking. Give me a thumbs up. Thank you. You have one type of monomer, example, rubber tire or saran wrap. Condensation, you have either plastic, that's where you have, oh, I didn't write it down here. And a condensation polymer has 2 different types of monomers reacting together. And a lot of times you're either forming an ester, not always, or an amide. Speaking about esters and amides, time out for a commercial from Dr. White. Don't forget, yesterday I talked about the extra credit project. And remember, it's 10 points, bonus points you can earn. How do you do that? You make a list of 10 different molecules that are found in items you can buy in your everyday life. Now, let me just open up the whole thing. Let me find it. All right, I have to do this. Sorry about the delay. I thought I had it on this machine. All right, everybody say extra credit project on your screen. Thank you. All right, again, you need to create a chart with 10. Remember, organic molecules, sodium chloride is inorganic. So sodium hydroxide and other things like that, which are found in the ingredients list of commercially available products. You can use a molecule only once in a chart, but you can get all up to 3 molecules per product. And to get full credit, all entries in the row must be correct. For each entry, name the product, name the molecule, and name one. If there are more than one functional group, you only have to name one. If there's only one, you have to name that one. And don't forget to put your name on the chart. But and here's an example: product, molecule, functional group, brand X wine, ethanol, alcohol. Now, there's certain molecules you can't use: sucrose, ethanol, isopropyl alcohol, acetone, ethyl acetate, propane, acetic acid, and methane. Certain products you can't use: beer, wine, vegetable oil, vinegar, gasoline, propane gas, natural gas, orange juice, milk, sugar, or butter, but you can use everything else. By the way, easy way to do this is look in your bathroom and also in your kitchen, and you'll find all you need. Or if you want to have fun, I don't know, with the pandemic, would you want to do this? But it's getting safer, maybe. Go to a local big box store and walk down the aisle where you find all your personal care items like shampoo, uh, skin conditioners, and things like that, skin lotions, and you'll find your 4 products real quick. If you take a cell phone, you can take pictures of the label and look at them back in the comfort of wherever. Anyways, this is important. Ingredients must appear on an ingredients list on the product. They must contain a functional group discussed in this class. It's due by the end of the day on the 26th of this month. I will not accept the late project uploaded as a PDF file or MS Word file. Now, this is optional. You don't have to do it, but if you want 10 points, do it. Now, beware, not all names on labels are IUPAC or common names. And simethicone, and students have put this down. Oh, and the ending ketone? No, it's a silicone compound. And use Google, or I can help you too. Now, my public service to you is before the project is due, the 26th, make your list and email it to me, and I'll check it. Common mistakes. Somebody sees something like sodium benzoate and they put it down as a carboxylic acid. No, it's a carboxylate anion. And those are some of the mistakes they make. Stick with functional groups you know. Why did I put that in there? When I didn't have it in there, people would find things, oh, that's a functional group, and totally mislabel it and get 0 point for that entry. Remember to have 10 things, and they all don't have to be different functional groups. I've had students that every one of those are alcohols or other functional groups, or a combination of only 2, or you can get more. It's up to you. Any questions about that? And that's my public service. Don't forget, it's 10, 10, 10 big points. Hold on. Time for Dr. White to be totally obnoxious. 10 big points. That was pretty obnoxious. Bad, Dr. White. But anyways, it will help your grade. It can't hurt. But you got to do it. And before you do it, so you do get your 10 points, send it to me and I'll check it and help you get them all right. But you got to do it. All right. Now, the other type of polymer, and I better make this visible to you, is a two types by physical properties. Thermoplastic, once formed, can be reheated. Example is polyester, like a water bottle, or the other one is saran wrap is a thermoplastic. There's no correlation between the chemistry and the physical properties. Now, you should also know a thermoset is a polymer once heated, cannot be reshaped. An example, rubber tires, phenolic resins, which I'll example your buttons, if they're not metal, are made of phenolic resins. And I worked at a company that made those. I actually have a patent in that stuff. Now, I talked about additional polymers, switches off here. You should know cross-linking by having chemical bonds between chains that makes the polymer have better physical properties, such as more rigid and other physical properties. That's how Goodyear invented rubber that we now use for car tires and other things. I talked about condensation polymers. Example, the switches off, polyesters, ester formation. Polyamides, example would be Kevlar. Polyurethane, we did a lab already with this. And phenol formaldehyde, which I did. All right, let me open up something. Let me close things first. All right, everybody see carbohydrates on your screen? Thank you. All right, and we talked about what is a carbohydrate. You should know it's a polyhydroxyaldehyde, polyhydroxyl ketone, or a compound that yields such upon hydrolysis, which starches do make glucose or sugars make fructose and glucose. You don't have to know the structure of fructose or glucose, but I do want you to know what it is. So here it is. Remember, this is how my software and a lot of things draw this aldehyde functional group. And here in fructose, I got carbons here, this is a ketone. So glucose has the aldehyde, fructose has a ketone. I gave you some definitions I didn't ask you to learn. However, there was one important disaccharide you should know. Sucrose is table sugar. And we switched to chirality. You should know chiral means Greek for handedness. And it's been about a couple of years ago, I had two students who spoke fluent Greek, and they confirmed that's what it means. Now, when we talk about chirality, I taught you about mirror images, and there's superimposable mirror images and non-superimposable. And the superimposable, I told you a story where I first had these slides, used to say super impossible until someone pointed it out. Dr. White was always first down in the spelling bee. And a superimposable mirror images, all points coincide when you lay them together, which my hands don't do. But non-superimposable, all points of the image and its mirror image don't coincide when you try and lay one on top of each other. And next, I talked in terms of handedness chirality. There's a chiral object, an object that is not identical to its mirror image, which means it has a non-superimposable mirror image. A chiral object, object that is identical to its mirror image. It has a superimposable mirror image. And we went through some examples of what's chiral, what's achiral. And if we look at the fact that my hands are mirror images, forget about the ring for now, and they're not superimposable. Now, if I had, this is going to be, hold on. Forget about these are carbons. Just think of them as, cute little models. And if I go like this, they're mirror images. There's a mirror right between. And notice how they line up and they're superimposable. So this object is an achiral object. And we went through different things in our daily life that are chiral or achiral. And let's think of one. Is your left shoe chiral or achiral? And the answer is chiral. If you take a look at your left shoe and put it in front of a mirror, it's your right shoe you see, and you can't superimpose them. Now, a quick way to know if something's chiral or achiral, if it has the word left or right in it, it's always going to be chiral. Handedness. So if I say I have my right shoe it's chiral. If I have a left winter glove, which I don't have, thank God I'm not using them right now, as soon as you see left, you know it's chiral. And if you draw the mirror image, you'll know it's non-superimposable. Another way of telling that is you have your left glove, you can't put it on your right hand and it won't work well unless it's mittens and it has a stuff on the back and a palm, you can't, vice versa. Now mittens or tube socks, you can put on either hands or feet, and that would be achiral. So we have that. And next I talked about a chiral center, or in this class, chiral carbon. That's a carbon atom in a molecule that has 4 different groups tetrahedrally bonded to it. And if I were to ask you, circle the chiral carbons in the following molecules. Let's do a couple. Again, circle the chiral carbons in each of the following. And why don't you do those two? Oh, we'll do one more after this. And when you're done, give me a thumbs up. Some of you are done, and we'll wait for everybody to finish. All right, I think is everybody finished? I think so. All right, when you're looking for chiral carbons, what are you looking for? A carbon with 4 different atoms or 4 different groups or a combination thereof. And if you see 2 or more of the same atom or group, you can't have a chiral carbon. If you have a carbon in a double bond or a triple bond, it can't be. So 3 hydrogens, that's out. 2 hydrogens, that's out. Oh, this might be, this might be. Notice this carbon is double bond, it's out. This one. Now, if I look at this carbon, I have a hydrogen chlorine. This I'll call R, and this I'll call R prime. It has 4 different groups. And same thing here. I have this hydrogen, this bromine. I have this as I'll call R prime. And now this is different, R. So I have hydrogen, bromine, R prime, R. This would have 4 different groups. So those would be the 2. And I shouldn't have done this. Let me do something. And that's how you would do it. Now, if we look at B, again, chiral carbon, anything with 4 different groups or 4 different atoms or a combination of 4 different groups or atoms. If you have 1 or more of the same atom or group, it can't be. This is out. Oops, still have my eraser. I just lost my hydrogens. This is out, this is out, this is out, this is out. Because it's got 2 hydrogens. If it has 2 or more, can't have 4 different groups or atoms. Now, if a carbon is in a double bond, it's out. Carbon oxygen or carbon carbon. Now, one thing I haven't done much, but that writing it this way is the same as writing it that way. A carbon with a hydrogen and a bromine on it. And it's got a methyl, this whole thing, hydrogen, bromine, that would be 1. Here I have hydrogen hydroxyl, this whole thing, and this, and they're different. And this would be 1. So those would be our 2. Oh, let's do one more because these are fun. Remember, this is a Fisher projection, and each one of these intersections is a carbon atom. There, 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 and there. And then the others are written. Circle the chiral carbons in that molecule. And when you're done, give me a thumbs up. All right, hopefully everybody's done. Let's take a look at this. Now, if a carbon has got 2 or more of the same group or atom, it can't be chiral. So this carbon, when I get a pen working, is out. Now, carbon in a double bond is out. Remember, 3 line, This means identical. This means really this. So that means this carbon's out. But this carbon has a hydrox group carbon, this R group and this R group. It's chiral. Same thing with this one, same thing with this one. Now let's look at this one. Dr. White can be sneaky. How many of you circled that? Don't raise your hand or your thumb, but it's got 2 hydrogens, so it can't be, it's out. And those are your 3 chiral carbons in that molecule. And that's how you do circle the chiral carbon. Now, I'm going to do something totally uncharacteristic for Dr. White. I think this is a good time to take a break and call it a quits for today. We'll continue tomorrow. But before I do that, I'm going to do a poll. I'm not going to change. I don't have time to change the question. But this is totally anonymous. But how many of you like where it says, are you done? Think of the question. How many of you like the review I did today and the extra work we did in fats and oils and polymers? Why don't you answer the following question? Yes, you liked it. No, you didn't. Well, it looks like everybody liked it. And come Thursday, you'll understand why I think you should like it. And with that, I'm going to say, gehen gesund, goodbye, bye. Don't forget, tomorrow we'll, instead of a lab, we'll have a full review of stuff today, of newer stuff for test 4. That's why I switched it. And then Thursday we'll do the lab, and then I'll let you out early, and you'll be able to start test number 4 early. You'll still have till next morning to hand it in. And with that, I can say, gehen gesund, be healthy. I'll see you tomorrow. Bye.